Today we're diving into the world of data preprocessing, focusing on a critical aspect, dealing with outliers. Outliers are data points that significantly differ from other observations. They can arise due to measurement errors, data entry mistakes, or genuine variability in your data. If not handled properly, outliers can skew your analysis and lead to misleading results. In this video, we'll explore why outliers matter, how to detect them, and practical strategies to manage them effectively. Let's start by understanding what outliers are and why they're so important in data science. Outliers can have a profound impact on your data analysis. They may distort statistical measures like mean and standard deviation, potentially leading to incorrect conclusions. For example, a single extreme value can shift the average, making your data appear more variable than it actually is. In predictive modeling, outliers can affect the performance of algorithms, especially those sensitive to data distribution. Understanding their influence is the first step toward making informed decisions during preprocessing. Now, let's look at how outliers typically appear in datasets. Outliers can emerge for various reasons. Sometimes they result from human errors, such as incorrect data entry or faulty measurements. Other times they reflect natural variations in the data, like rare but valid events. It's important to distinguish between these causes because your approach to handling outliers may differ. For example, a typo in a dataset should be corrected or removed, while rare but real observation might need to be retained. Next, let's explore how to detect these unusual data points. One of the simplest ways to spot outliers is through visualization. Tools like box plots, scatter plots, and histograms can quickly reveal data points that stand out from the rest. For instance, in a box plot, outliers appear as dots outside the whiskers. Visual methods are intuitive and provide a quick overview, but they may not always capture all outliers, especially in large or complex datasets. Let's see how statistical methods can complement visual detection. Statistical techniques offer a more systematic approach to detecting outliers. Common methods include using the z-score, which measures how many standard deviations a data point is from the mean, and the interquartile range IQR, which identifies values that fall outside the typical spread of the data. These methods are especially useful for large datasets where visual inspection isn't practical. By setting thresholds, you can flag data points that are likely outliers for further investigation. Z-score is a popular method for identifying outliers in numerical data. It calculates how far a data point is from the mean, measured in standard deviations. Typically, a z-score above 3 or below is considered an outlier. This method works best for data that follows a normal distribution. However, it's important to remember that not all datasets are normally distributed, so always check your data's characteristics before applying this technique. Interquartile range, or IQR, is another robust method for detecting outliers. It focuses on the middle 50% of your data between the first and third quartiles. Any value that falls below Q1 minus 1.5 times the IQR or above Q3 plus 1.5 times the IQR is flagged as an outlier. This method is less sensitive to extreme values and works well for skewed data. It's widely used in box plots and is a staple in exploratory data analysis. Statistical methods are powerful. Domain knowledge is crucial in outlier detection. Sometimes what appears to be an outlier statistically may be a valid and important observation in your field. For example, a sudden spike in sales during a holiday season isn't an error. It's a meaningful event. Collaborating with subject matter experts helps ensure that you don't inadvertently remove valuable data points. Now let's discuss strategies for handling outliers once they've been identified. Once you've identified outliers, you have several options for handling them. You can remove them, transform them, or keep them depending on the context. Removing outliers is common when they're due to errors, but be cautious. Removing too many can bias your results. Transforming outliers, such as by applying a log transformation, can reduce their impact. In some cases, it's best to keep outliers, especially if they represent real, meaningful phenomena. Moving outliers is appropriate when they're clearly due to errors or irrelevant to your analysis. For example, a negative age in a dataset about people is likely a mistake. However, always document your decisions and consider the potential impact on your analysis. Removing outliers can make your data cleaner, but it may also remove important information if not done carefully. Sometimes, instead of removing outliers, you can transform them to reduce their influence. Common transformations include logarithmic, square root, or Box-Cox transformations. These methods can help normalize the data and make outliers less extreme. Transformations are especially useful when you want to retain all data points but minimize their impact on statistical models. Another approach is to replace outliers with more reasonable values, a process known as imputation. For instance, you might substitute an outlier with the median or mean of the data. This method preserves the dataset size and can be useful when outliers are due to errors. However, imputation should be used with caution, as it can introduce bias if not done thoughtfully. Capping and flooring, also known as winsorization, involves setting extreme values to a specified percentile. For example, values above the 95th percentile are set to the 95th percentile value, and those below the 5th percentile are set to the 5th percentile value. This technique limits the influence of outliers without removing them entirely, maintaining the overall structure of the data. Some statistical methods are less sensitive to outliers by design. For example, using the median instead of the mean or employing robust regression techniques can help minimize the impact of extreme values. These methods are particularly useful when you expect outliers to be present and want to reduce their effect on your analysis. Machine learning, outliers can affect model training and prediction accuracy. Some algorithms, like decision trees, are more robust to outliers, while others, like linear regression, are more sensitive. It's important to understand how your chosen algorithm handles outliers and preprocess your data accordingly. Sometimes specialized algorithms for anomaly detection can be used to identify and handle outliers automatically. Transparency is key in data preprocessing. Always document how you handle outliers, including the methods used and the rationale behind your decisions. This practice ensures reproducibility and helps others understand your analysis. Good documentation is especially important when sharing results with stakeholders or collaborating with a team. Let's consider a practical example. In a retail sales dataset, you might find unusually high sales during holiday seasons. These are not errors but important events. Removing them would distort your analysis. Instead, you might flag these as special cases or use robust statistical methods to account for their impact. This example highlights the importance of context in handling outliers. In sensor data, outliers often result from hardware malfunctions or environmental noise. For instance, a temperature sensor might record an impossible value due to a glitch. In such cases, it's appropriate to remove or correct these outliers to ensure data quality. This scenario demonstrates the need for careful inspection and domain expertise. With large datasets, manual outlier detection becomes impractical. Automated tools and algorithms can help flag potential outliers for review. Techniques like clustering, isolation forests, and autoencoders are increasingly used in modern data preprocessing pipelines. Automation saves time and ensures consistency, but always review flagged data points before making final decisions. Handling outliers isn't just a technical decision, it can have ethical implications. Removing or altering data points can affect the fairness and accuracy of your analysis, especially in sensitive fields like healthcare or finance. Always consider the broader impact of your preprocessing choices and strive for transparency and fairness in your work. Wrap up: dealing with outliers is a crucial part of data preprocessing. Start by understanding your data and the context of outliers. Use a combination of visual, statistical, and domain-driven methods to detect them. Choose handling strategies that fit your analysis goals and always document your process. By following these best practices, you'll ensure your data is clean, reliable, and ready for insightful analysis.